Hi everybody, I'm Ali El Kamel, an assistant professor and a member of the Plans Research Lab from the University of Sousse, a great university in Tunisia. I'm conducting research in improving the quality of service, the robustness and the security of networks generally, and in SDN-enabled networks particularly. Today I'm giving a talk entitled Improving the Routing Process in SDN using a combination of the evidence theory and machine learning. This is mainly a presentation of my last work dealing with the use of artificial intelligence in mitigating the DOS attacks. My work is mainly done in the context of SDN due to several advantages which are provided progressively within this presentation. Let's begin. At the beginning, let's talk about the conventional network. An equipment legacy network consists of three layers, which are the data layer, the control layer, and the application layer. All of them combined in the same unit. The control plane must take decision on packet forwarding towards the destination based on the network policies. So, the control plane builds routing and switching tables and uses them to keep frames forwarding at point-to-point context and packets delivery at end-to-end scope. Another issue in conventional networks is associated to the necessity of exchanging network states periodically to ensure efficient routing. For example, the use of OSPF as a dynamic routing protocol requires periodically to exchange advertised messages between all nodes from the same area, which may overload the network, leading to a disruptive service, sometimes with a significant impact on network availability. Due to previously listed issues of conventional networks, the purpose of new paradigm to solve them must not be delayed. Hence, SDN is officially proposed in 2009 to deal with the matter of overwhelming the forwarding layer with control traffic and to leverage taking decisions efficiently by centralizing the control plan as well as the application plan, but leaving the data plan distributed. This is SDN, but what is the problem? Mainly, the centralization of the control capabilities raises many security issues. In fact, since the control plan is programmable, this opens a large door for vulnerabilities. SDN can attract a big vector of vulnerabilities, especially distributed denial of service. DDoS can target the controller. In fact, a malicious node can inject a huge number of new flows with distinct headers through compromised hosts. As a result, and since not much will be found in flow tables, requests are communicated to the controller for further processing. As the number of requests goes up, the controller can no longer reply to requests and so it is unavailable, leading to network breakdown. OpenFlow itself can be a source of attacks. All specifications of OpenFlow advertise the use of TLS but optionally. Skipping this optionally is mainly caused by its process complexity, and this opens a big door to man-in-the-middle attacks. Finally, switches can be attacked by flooding-based DOSes. This attack consists of installing a huge number of flow rules which exhausted the TCAM capabilities. TCAMs are designed with limited space between 1500 until 3000 flow rules for a maximum. This can be done either through a compromised controller or using vulnerabilities of OpenFlow. Unfortunately, the DOS attacks still occur at increasing rate with most sophisticated techniques. The matter is not a question of lack of protection techniques, but it is mainly associated to the strategy used to fight attacks. So the question is not what to use to protect, it is how to protect. Current strategies are defensive-oriented, which means that they are based on react after the occurrence of attacks. Further, current techniques such as ciphering through RSA, IES, tunneling through IPsec, VPN, MPLS, and access control are mostly considered heavy and introduces a significant overhead on communications. So, those techniques are no longer recommended for new real-time applications with strong QoS requirements. Today, we think that we should migrate to offensive-oriented techniques, which can anticipate the occurrence of attacks at early stage and can take prior preventive decisions to reduce the impact of threats or why not neutralize them. Offensive-oriented security is a new orientation in security which is based on predicting the occurrence of attacks by monitoring either traffic behaviors or node behaviors. Any abnormal behavior in flows may be explained as an attempt of attack. Also, any misbehaving node can be classified as a compromised or a compromising node and can be a source of attacks. Using historical evaluation, we can estimate the state of a node in the future by predicting its future behavior. This can be done using artificial intelligence. Artificial intelligence is a promising solution to achieve this aim. This work puts forward a trusted routing scheme TLS in SDN that aims to establish secure routes by dynamically escaping from malicious switches during routing process. Malicious switches are identified using the DS evidence theory and the SVM algorithm. Indeed, SVM allows to classify a switch as benign, malicious, or uncertain according to a per-switch global trust vector. The global trust vector consists of a set of trust degrees computed throughout an integration of direct and indirect trust values. The direct trust value is computed by the controller using a set of trust factors directly gathered from each switch. The indirect trust value is based on the multi-hop trust transitivity rule, which means that if A trusts B and B trusts C, then A trusts C, and involves many side recommendations from the switch's neighbors. Integration process is achieved in accordance with the DS combination rule. The resulting trust vector is inputted to a multi-class SVM algorithm which recognizes the switch as benign, malicious, or uncertain. Beyond the classification of switches, a trust graph is established by the controller and used to find the most trusted path joining endpoints by application of a new algorithm denoted Trust Path First, TPF. TPF is based on a modified version of the Dijkstra algorithm to support the computation of the most trusted paths. We introduce a new link cost as shown here. TPF is able to reroute flows far from compromised nodes, which are then isolated from the rest of the network through a network healing mechanism which aims at avoiding the propagation of the DDoS attacks to the whole network. The network healing mechanism aims at restoring a steady state of the network. We consider a training dataset of 5,000 samples obtained from the Kaggle repository. In this dataset, 75% of samples are used for training, while the rest are used to validate the model. We evaluate the classification through the following metrics: precision, recall, and F1 score. After being trained, the model offers a precision of 0.93 to classify malicious nodes correctly, 0.9 for uncertain nodes, and 0.84 to recognize benign nodes. The model is able to deliver an acceptable TP rates, which are 67% for malicious class, 96% for uncertain class, and 89% for B class. As shown in the results, the throughput offered remains nearly close to 140 kilobytes per second, while it goes under 120 kilobits per second for SPF when multiple attacks happen. TPF ensures reduced end-to-end delay for packets even if multiple attacks happen simultaneously. At 100 seconds, the disparity between the delays of SPF and TPF exceeds 10 milliseconds for the scenario of two attacks and reaches 7.5 milliseconds for single attack point. In the conclusion, AI-assisted security can improve the protection of networks against most attacks, especially DDoS attacks. It is necessary to migrate from defensive-oriented security to offensive-oriented security, and it is also necessary to migrate from data-driven security to node-driven security. Mainly, data forwarding and security must be combined and not tackled separately, and this way TPF is proposed in spite of SPF. For more information, you can contact me as follows.